is my pleasure to introduce Professor Mohammed Mogtaba of Majma University, KSA and AIM, South Africa. He works in partial differential equation, probability theory, and stochastic process, and in particular in stochastic homogenization. Please.
Thank you very much. Good morning to everyone. It is, of course, my great pleasure to be among you, and I would like to thank the organizers for inviting me to be a part of such a great. My talk will be on homogenization and correctors. If time permits me, I will discuss also the correctors, homogenization and correctors for linear stochastic equations in periodically proliferated domains with non-linear Robin conditions. Here are the outlines of my talk. I will give some introductions, setting the problem. I will state my main results, give some notations on probability spaces, functional spaces, and the unfolding operators, and some properties of the unfolding operators. I will also outlines the tightness of probability measures generated by the solution of our original problem. I will also explain the applications of Prokhorov and Skorokhov theorems, and after that I will take the homogenization results to the considered problem. So I will go directly to my introductions. I will spend maybe 2 to 3 minutes about the challenges that we shall face in obtaining the homogenization results. Actually, when dealing with stochastic partial differential equations, and you have oscillations on the boundary and on the solutions, the coefficients, the first obstacle that we can face is the dependence of noise on the differential equations. Here, as example, I'm going to use the Wiener process. When the partial differential equations depending on some noises, and the noise and the solutions are both depending on a common probability space. So the challenge here is when you are looking for some compactness, the compactness always constructing a new probability space. So you're going to lose the probability space that your original problem is defined on. So in this case, we use a Prokhorov and Skorokhov process to construct a new probability space with a new Wiener process. But we have to prove that the new Wiener process that you constructed is actually a Wiener process and actually satisfy your original problem. So in this case, we're going to transform the original problem to a new problem with a strong convergences through the probabilistic compactness. This is the main challenge when dealing with stochastic PDEs. And here we are not considering that the coefficients is oscillating on the random variable, as Petriski did for his lectures. Here is the coefficients and solution are oscillated on the spatial variable. But the stochastic partial differential equations itself, as I said, depend on some noises which make the use of a deterministic compactness is not possible. That's why we have to go through some stochastic calculus. Also, one of the challenges that in the problem we are considering, the variation formulations contain some boundary terms on the boundary of the holes. So these integrals, some boundary integrals, will not allow us to pass to the limit when the surface is varying. So good thing that we use periodic unfolding methods to define a periodic boundary of unfolding operators so that we transfer this integral to a fixed integral on a fixed surface. So the last challenge that we shall face is when passing to the limit on the stochastic integrals. So hopefully through these lectures, we will go through all these obstacles and see how to overcome them one by one. So now regarding the homogenization of SPDEs, homogenization of SPDEs is still a few results when you compare with homogenization and the progress on homogenization. There are not so many results are in these directions. Actually, the first work that, as far as we know, is the work of Pensosan in 1991. He obtained a homogenization of stochastic partial differential equations. The model that he considered was parabolic, and he obtained a homogenization results. I think it was in a conference book. I'm not sure, but I have the paper. His result was followed by Sangu in 2002. He also obtained a homogenization. He used the technique of Marchenko and Kozlov in 2002, and he obtained homogenization results. So their work from 2004 to 2013 by many scientists. I'm just mentioning few of them here. There are very interesting results, and all the results up to 2013 was on the parabolic stochastic differential equations. From 2015 to 19, myself and Sangu obtained several results was on the hyperbolic stochastic differential equations, and we use almost all the classical homogenization techniques. We use the Tatar methods, we use the two-scale methods, and we used the asymptotic expansion methods by Bensusan, Lyons, and in their books. And in the 2019 and 20, Carlsen and his colleagues, they obtained, I think there were two papers published by them on the homogenization of not really stochastic partial differential equations, but they studied the conservation laws of stochastic differential equations. They obtained interesting results, and they use the same technique, stochastic calculus that we are considering. And myself and my students in the 2020 and in this year, we used the periodic unfolding methods. We obtained results on fixed and perforated domains for stochastic partial differential equations. So now here is the problem that we are considering is, as you can see, the stochastic partial differential equations. The differential equation itself is a linear with a non-linear Robin conditions on the holes. The perforated domains, we are taking the same structures that is considered by Soronescu, Donato, and Zaki. This is a linear stochastic differential equation with a non-linear Robin condition that we shall study. So here is just epsilon is a sequence of positive number that allows to go to 0, and T is always positive. D is an open domain. W is the m-dimensional standard winner process, and defined in a given complete probability space. As I mentioned, the perforated domains, I'm not stating it here due to the shortage in time, but in the document is stated and explained very well, but we are taking the same structures as done by Soronescu, Donato, Gresso, and Zaki. So here are the assumptions on the data of our problem. Of course, the matrix is in L infinity and coercive. The functions capital F and capital G are both in L2. The functions G, which is in the boundary, is also in the L2 of the boundary of the holes cross 0T. And the differential G epsilon W is understood in the sense of E2 or I2 as here are the main assumptions on the nonlinear term. The nonlinear terms, we assume that H is to be a continuous differentiable function in the first argument. We also assume that H is monotonously non-decreasing in the first argument. And we assume that it is zero when the first argument is zero. And for all positive constants, we assume that to satisfy this growth here. Of course, from these assumptions, we can see that H of S times S is always positive. These assumptions are actually very important in obtaining the existence and uniqueness, and also is very important when passing to the limiting on the nonlinear term. So as far as for the existence and uniqueness for the solution of the considered problems, myself and Noor, we proved the existence and uniqueness for a more general form for nonlinear stochastic equations in a domain with holes. We consider the Robin conditions on the holes, and the result is hopefully to appear soon. So our model is well posed. Here are the main results that we shall study. We shall show that with the assumptions R1 to R5 and also the weak convergences that are assumed on the data, we shall obtain the existence of a probability, new probability space, and in new random variables indexed by epsilon j, which is a couple of the solution and the winner process, and a couple of the limits for these both subsequences, such that we have a strong convergence, P almost surely convergence on the W epsilon j and Q. The function Q is actually the macroscopic part, the macroscopic representation of the solution of the original problem. And soon we shall identify what do we mean by Q tilde of U epsilons. And not only that, we also have these convergences of the unfolding and the boundary unfolding operators of the solution of our original problem. And all these convergences are P almost surely convergences. And the limit W hat and U are actually satisfy the homogenized problem. The homogenized problem we denoted by R. We also seen we shall soon see R, which is a homogenized problem to our model. We shall also talk about the corrector, the strong convergence of the solution of our original problem. Also, the convergence is P almost surely. Now we have here some probability functional spaces I'm going to introduce. I will start by the well-known evaluation Banach space for functions of x and t is defined for all measurable functions v from 0 to t to x and p integrable with this norm here. And when p equal infinity, we also have the corresponding Banach space with it is corresponding norm. So this is very well known. It's the Banach space. And from this, I'm going to state the probabilistic Banach space defined as a set of all random functions v from omega 0 t to x, such as that this function is measurable with respect to the sample variable and time for almost all t v, and ft is measurable, and ft measurable in omega. We induce this space with the this norm here, norm containing the expectation, which is actually the integration of the random variable with respect to the probability measure that associated with the probability space. When p equal infinity, we also have the corresponding Banach probabilistic Banach space. So here I'm also going to talk a bit about the time-dependent unfolding operators. As it's known that the unfolding operator itself has been introduced by Saranescu, Damrian, and Creso. It has been introduced in 2002 to study homogenization of partial differential equations in fixed domains. And they later, in 2007, developed or extended their unfolding operators to study problems in perforated domains. The first extension of the periodic unfolding operators to study time-dependent problems was by Saranescu and her students in the 2011, I guess, or 2009. Now I had a doubt, but I think it's 2011. And Donato and the Young, they study homogenization for evolution problems. So they developed the time-dependent unfolding operators in perforated domains. And myself, I used these techniques to obtain homogenization results in 2019 for a fixed domain. And last year, we'll study homogenization of linear in perforated domains, but it was not with nonlinear Robin conditions. So myself and my students know. So here are some of the properties and definitions of the periodic unfolding operators in time-dependent problems. So for all functions defined in LQ0T, LP 0T, LQ, D epsilon, as I said, D epsilon is the perforated domains. We define the unfolding operators by this map, and we define as extension of functions that satisfies this equation here. So here is the definition of the periodic unfolding operators to treat time-dependent problems. Here are some of the properties that you are going to use. For any fixed functions, the periodic unfolding operator is strongly converging in the equation 11. And for any strongly converging sequences, the periodic unfolding is also strongly converging. So for more details in the documents, of course, the details of and the proof of this is there, but it's originally in the work of Professor Donato and Z. Young. Yeah. So also the macro and micro decompositions, we adopted the macro and micro decomposition obtained by Saranescu in 2011 from for functions in spatial domain to function evolution domain or time-dependent problems. I'm here only stating that any function on this space in LP0TL, Q, D epsilon can be decomposed to two functions. Q is always designed to capture the macro scale part of the function, and R epsilon is the remainder captures the oscillations. So here are the Q and R that I mentioned on my main results. Now this lemma is on the deterministic lemma. We obtain the probabilistic lemma equivalent to this one when considering random variables. This lemma says that for any bounded functions on LP0TH1, we can find a couple of functions, phi and phi hat, so that phi and phi hat on the given domain here in H1 and the domain L2DH pair Y, such that we have the convergences and the lemma. So this lemma, as I said, is proved by Professor Donato, but we are studying the equivalence in the stochastic or in the probabilistic sense. So here are the main properties of the time-dependent unfolding operators. Now we are giving some properties and definition for the boundary time-dependent unfolding operator. Here is the definition. We define it in an analogy way to the case of spatial or the elliptic problems. Here we define the boundary unfolding operators as a map, also in equivalent to the one we define on the domain instead of the surface. So also we have the properties of the domain of the periodic or the boundary periodic unfolding. You have the strong convergence for any fixed functions, and if the function is weakly convergent, then we have the convergence here in lemma 3. We also proved this lemma for any random functions phi. For any random functions phi and deterministic function g, we can show that this integral equation is converging strongly, p almost surely. The proof is a bit technical. We are not stated here, but in the document is also there. So I actually, most of the preliminary results, I'm not stating the proof due to the short in time, but I will explain how do we get there. But in the documents, I shall submit to the organizer if it is needed. We also have this P almost surely convergence, and we have the boundedness on G. This is actually needed when obtaining the a priori estimates for our original problem. Now, this theorem, this is the main theorem allow us to pass to the limit on the nonlinear term on the surface. So this theorem was proved in the deterministic for elliptic problems, but for our case, it needs some strong convergences, and the strong convergence for stochastic we will not have by the deterministic compactness results. So this is one of the main obstacles that we face when obtaining the homogenizer results. So we need to use Correctors and Prochlord theorems to obtain some strong convergence on our solution, so that we can obtain this limit here, this limit on the boundary unfolding operators to the nonlinear term h of V epsilons. So the proof is also technical and a bit long, but we have proved it for any random functions that on the corresponding space to L20T H10D. So the first results we obtain is these a priori estimates. The tools that we used I2 lemma, and we use some appropriate stopping time. And we use the variation formulation to obtain the estimates 14, 15, 16 to our problem. We also proved that the macro and micro representation of the solution satisfy the estimate from 17 to 20. And this finite difference of the macros is obtained, and the main idea of obtaining these estimates here is actually because our problem is linear, and the solution is represented as a decomposition of Q and R. So since the problem is linear, we can say that Q is actually satisfy our original problem, and we used once again I2's lemma, and we obtain these estimates, which is of great importance when studying Prochlord and Skorokhod compactness results. So now I have 14, 15, 16, and 21. These estimates, the solution of the problem satisfy these estimates. These will be used when defining a space on the solution of the original problem to obtain a tightness. So now from the estimates, from these estimates here, 17 to 20, we have that the convergences of the oscillated part of the solution of the original problems, and among them we have 24. The convergence 24 is actually strong convergence, and we are looking for strong convergence to the solution of the problem, but this is the oscillated part. So now, in order to obtain strong convergence to the solution of the problem, we need a strong convergence on the macro representation of the solution. But for the strong convergence for the macro representation of the solutions, we are not able to use the deterministic, as it is random and defined in a common probability space with the winner process. So Q is defined on a common probability space together with the winner process. So we are not able to use deterministic compactness to obtain some strong convergences on Q. So we had to prove some tightness on Q, and from that we can get strong convergences. And this is the topic of the section 3. So the third section here is about the tightness. So for the tightness, we have first to define the space Z. This is the space Z. As you can see, the set of all functions satisfies the estimates. These three estimates, this in the space that satisfied by any functions belong to Z are satisfied by the solution of our problem. So before we go ahead, we can say the solution of our problem, or in particularly the macro scale part, is belong to Z. So now I have the space that where our solution belongs to. So now we proved that this set I define Z is actually a compact subset of L20T, L2D. The space. The proof of this lemma is technical, but we used the Simon's lemma and some ideas of taken from the paper of Penso-san, the 1991. So we use these ideas to prove that the constructed space is actually compact in L2, 0D, 0T, L2D. So, but this space is concerning only the solution. We have also to define a space on the winner process. So for that, we define the tightness of any probability measure. What do we mean by a tight probability measure? So given any set Y and B of Y is the separable Banach space, I had to mention it, and B is the set of all porous sets of Y. So any sequence or family of probability measure defined on this set is tight if we can find a compact subset of Y such that for each epsilon, the probability of K epsilon is greater than or equal to 1 minus epsilon. This what do we mean by tight? So if any elements of the family can satisfy the probability of a compact subset of Y is greater than or equal to 1 minus epsilon. So we are going to use these definitions on Prokhorov lemma. Prokhorov lemma says any sequence of probability measures on the separable Banach space with its poral sets is tight if and only if it is relatively compact. So if we can prove that a set that contains the solution of our original problem and also contains the winner process that is compact, then I can say the probability measures of these sets is actually relatively compact. And the relatively compact is only giving us a sort of weak convergence, but we are looking for some strong convergences. This is by scorecard lemma. Scorecard lemma says if a probability measure is weakly convergent, which is mean relatively compact, to a probability measure mu, then we can find a sequence of random variables defined on a common probability space, such that the probability law of the sequence is mu n, which is the probability measures. And the probability law of xi, which is the limit, is actually the limit of the probability measure, such that this sequence is strongly convergent. So now I want to emphasize that if we can construct a family of probability measures on the solution of our problem and show that it's tight, we can construct a we can construct a subsequence which is weakly convergent, and then we can use Correctors lemma to obtain some sort of strong convergences. So here is the application. Here I'm going to define a set on the solution of our original problem. I'm defining C0TRM to be the set that containing the winner process. And I'm defining L20T, L2D as a set that containing the solution of our original problem. As I said, Z is compact in this space. So I'm defining a functions, psi epsilons, by this relation here. This relation shows that the functions take the random, the sample random variables, omega, to the couple of the winner process and the solution of the problem. And I'm defining the probability measures by the pullback of these functions. So now I want to prove that this constructed probability measures is tight. So this is in this lemma. The lemma is proved also in the documents. This is time. So yeah, I'm not here. It has been proved, but it's technical and a bit long. So the proof is also on the documents. But now I have that probability measures constructed by the solution of our problem, which is tight. So now I will use the tightness of the probability measures and apply Prokhorov's theorem. Prokhorov's theorem now is enable us to extract a subsequence of this probability measure, and that is weakly convergent to some measure on the same set X. So since I have weak convergence, so Correctors lemma facilitates the finding of a probability space, which is new probability space, and valued random variables. So as I said, the random variables now I'm considering is the random variables of the macroscopic parts and the solution and the winner process. And a limit for that, such that the probability law of the sequence is pi epsilon and the probability law of the limit is pi. And I have the strong convergence that I'm looking for in 25 and 26. Now I have strong convergence on the macroscopic part of the solution of our problem. And from this strong convergence, I can use now the properties of the unfolding operator and this convergence here in 27. And now I have strong convergence on the macroscopic, and previously I have a strong convergence on the remainder. Now I have a strong convergence on the solution of the problem. But the issue here is what of the sequence, the constructed sequence, W epsilon J and Q. So actually this has been shown in the documents that is actually satisfies the problem that you are looking for. So now I have a new problem. The new problem I have of course, satisfy all the priori estimates and all the weak convergences, and furthermore, satisfies the strong convergences on the solution of our original problem here. And also, I have the strong convergence of the winner process. So now I can say I'm ready to study the homogenization results to our problem. So here is the weak formulation. Here is a weak formulation to the linear stochastic differential equations that we are studying. I omitted the epsilon j just for simplicity. Instead, I omitted the j from the index epsilon. So just for simplicity, because I have the same problem. So also because I'm thinking of the time, but the limits for all the terms into 29s, I will just talk how do we find them. I have a weak convergence on the unfolding, and I have a strong convergence here. I can pass to the limit in the first term. So also in the second term, I pass to the limit in the usual sense. I have a weak convergence on the gradient, and I have a strong convergence on the gradient of phi. So as far as the nonlinear term, I use the lemma. I mentioned the compact lemma, that the compactness lemma I developed from the theorem of Soronisco, Donato, and Zaki. So we are also able to pass to the limit in the third term, which is containing the nonlinear term on the surface, on the boundary of the surface. So for the initial also term, for the first term on the right hand side, also the passing to the limit, it's not a big deal. Also the second and the third on the right hand side. So the main challenge here, which I'm going to take time on it, how to pass to the limit on the stochastic integral. So since I have a winner process, d epsilon j, and I have some weak convergence on G and strong convergence on phi. So here I will only take care of the convergence of the stochastic integral because of the time. So here's just the one I was talking about. Since my solution from the estimate 14, 16, and lemma 2, I can find existence of U and U hat. And I also have all the subsequences and convergences that I stated in the theorem. So, and I can pass to the limit in all. Here I'm going to talk now about the convergence on the stochastic term. So for the stochastic term, I will write it, split it into two integrals, as in the right-hand side of the equation 30. So I will first prove that the first term on the right-hand side of 30 is actually converging to 0. But as it's known that this variation, W epsilon and W hat, has an unbounded variation. It is a winner process. So so in order to take advantage of the definition of the strong convergence that I obtained from Brokhrov's lemma, I will define some regularization of the modifier on the unfolding operator T epsilon star. So I'm going to define here the modifier. So this modifier of the functions T epsilon star, I will define it so that satisfy the usual conditions, that is differentiable on time, and that is bounded by the boundedness of the function itself, and also strongly convergent. So the modifier I'm considering satisfies these three conditions: is differentiable on time, and also bounded and strongly convergent. So now I'm gonna the first term in 30 here, the first term on the right hand side, I'm gonna write it as this equation here. I will add and subtract the modifier, and I will have the two terms on the right hand side of 34. Now I will just deal with the two terms on the right hand side of 34. So for the first term on the right hand side of 24, I have a function that is bounded by the modifier function is bounded, and I have a strong convergence of these functions. So I will use the so-called Borchardt DV inequality. The BDG inequality is actually transfers the bound of the first integral into integral that does not contain W anymore. It actually contains dt instead of dw. So the second term in the right-hand side of 34 is bounded by two functions now. Sigma 1 of lambda, why? Because the function, as I said, is bounded, which converges to 0 as lambda goes to 0. This is the second term. In the first term, in the same relation, we take advantage of the differentiability. Now, the first term, I know that the modifier is differentiable in time. So the first term now is, the second term goes to 0. Here is the first term in 34. The first term on the right hand 34, I will differentiate by parts. I will get the two integrals on the right hand side of 35. For the first one, is bounded by two functions. But I have strong convergence here. I have strong convergence. And I also have strong convergence on the winner process by Skorokhod and Prokhrov convergences. And I also have a boundedness on the modifier. So both terms, I can write them as sigma 2 of lambda eta 1 of epsilon, so that eta 1 of epsilon goes to 0 when epsilon goes to 0. And eta 1 is bounded. Also two terms also converges to 0. So now I can go back in, and now I can say that the first term on the right hand of 30 is actually converges to 0. So now the limit on the stochastic integral can have this form 36. As you can see in 36, I do not have any oscillations on the winner process. I have no oscillation on the winner process. Now the passage to the limit is readily by a result, by a theorem in the book of Rzewski. So now I can pass to the limit, and I can have the corresponding limit on the stochastic integral. So having the limit on the stochastic integral, I can obtain it as follows. Now I'm adding 1 over lambda because it is on the weak formulations. Now I have theta, which is the density proportion of the reference cell and the body. So now I have the convergence 37. I can say this is weak formulation of the limits of my problem. As I said, I passed to the limit on all terms. I passed all terms in 38. Yes. Now here I have the corresponding equations. With the corresponding equation 39, of course, there is some few calculations and putting appropriate test functions. I did not do that, as it has been done and very clear, I guess. Also in the document, it is there stated. Now I have the limit of my problem, but this limit is up to a subsequence. So to have the limit on the whole sequence, I will take advantage of the uniqueness of strong probability solutions, and then up to distribution or probability law, the whole sequence of the solutions converges to the solution of the problem R. Thus now I obtain the solution, the homogenization results corresponding to my heterogeneous model. Now I will just talk about the corrector results.
One minute, please.
How many minutes?
It's finished, okay? 2 minutes. The time is
2 minutes.
But anyway, 2 minutes, okay.
Okay, no, I actually finished. I just want to talk about, I'm sorry. Yes. Yeah, here we stated the correct results. It's due to time. I did not present it because I checked yesterday and I find that it will not be possible for me to talk about the correct results. But we find this correct result. We first obtain some energy convergence, convergence for the solution and the homogeneous problems, and we use the Aitos lemma once again, and we obtain some sort of strong convergences with the unfolding operator. So just say thank you very much.
Thank you
For listening.
Interesting talk. Any question? Any remark? If some remark, you can write in chat. Okay, it seems no question or remark. Thank you again.